There we go.
So how are we doing today? You guys having a good day? All stressed out and everything? A little tired? Yeah. Well, I got the email that I've been not waiting for. Over Christmas break, I bought some outside, my boat used ones, about $18,000 worth, okay? And being cheap, I decided to find my own shipper, yellow freight, rather than FedEx or whatever. So it was like the difference between $800 for shipping and $350, okay? And I knew liability was a little bit over, but I figured, well, I'm not gonna lose them or anything like that. And sure as hell they lost them. And so I've been screwing around with them since January 3rd, I guess it was, or 4th, trying to find them, and they can't find them, and they don't know where they lost them. They think they lost them in Virginia or North Carolina, but they still can't figure out where they're at. And so they finally gave up on finding them. And so I was just hoping that they'd get with me and say, okay, we'll reimburse you for your invoice amount. You know how much they're offering? $326. $18,000 loss because they're punching counting fools. So, I'm just ticked off. I don't know what to do. If you ever see on television people going postal or something, you know, they'll be me here pretty soon. I don't know what to do. I hope they find them. That's all I can say. I think, you know, best thing I can do, or about the only thing I can do, because legally they have their terms and conditions, and I call it we get out of it. But I just like to go there, just go to where they think they lost it and say, okay guys, let me look around, let me find them. They're here somewhere. You don't just lose a pallet full of stuff. It doesn't disappear or get caught in the cracks in the floor. You lost it. It's got to be somewhere. They're going to find them eventually. And then they'll turn around and sell them on eBay or something and make a bunch of money off it. That's probably what's already happened. So, if you're having a bad day, just think of me. Today. That's just today. I got ripped off on something here a couple weeks ago that cost me about 10 grand, so it happens, but it really sucks. So we are in chapter 15, of course. How can you forget? Today we're going to continue talking about what we started yesterday, the regiochemistry and the reactivity of these substituents on the benzene ring. But before I do that, I can tell Yuki he's really into his problem set, and I need to go over a few things. So tomorrow, as I promised yesterday, I want to use lab time, at least an hour and a half or whatever, to go over problem set kind of questions, maybe some other questions, example problems, this kind of thing. So I realize that we've been going through a lot of material real quick here. Trust me, it's not real fast compared to what you're going to experience in a few years, but it's, you know, for what we're used to, it's a lot of material. And so I want to do that. I know you got an exam coming up next week, so I hope you can get ready for that as well. Anyway, I can. So no lab tomorrow. And so what does that mean as far as lab goes? Long term, some other things are going to have to change because we got a bunch of multi-week labs left. And if I delay the start of this 2-week lab until after spring break, then, you know, if it puts the squeeze on, I'm going to have to cancel a 2-week lab or make our 3-week lab a 2-week lab at the end. I don't know. We'll figure that out. I haven't given it much thought. I had other problems this morning. But, so yeah, no lab tomorrow. Instead, we'll meet, I guess, in here. And what time? 8:30. What do you guys want?
We don't get out of dip until 8:30.
Well, okay, so yeah, it doesn't matter to me, I guess, I'm just curious, what works
Oh,
guys?
that was
8 better for you?
9 sounds
No? 9 o'clock?
I mean, you can do it till 11, so.
It's not gonna be 2 hours unless you guys have a bunch of questions. If you're like one of the 22 classes, it takes about 5 minutes because they wouldn't have any questions. So guys have been there. Yeah, it's almost the anniversary. I think it was, well, it's still a few weeks away. 7th, I think, of March is when we found out that things were gonna get canceled last spring, so it was, first week of March. But, okay, well, anyway, so that, and I did give you in your handout that revised lecture schedule here. It really only affects like yesterday, today, and Monday. No big difference here, but I just wanted you to see it. So yesterday we covered sections 7 and 8. Actually, we finished up 6 and then covered 7 and 8. And today our goal is to go over 9 and 10, which we're going to do. Shouldn't be a problem. And then when we come back next week, we're going to, on Monday, cover essentially sections 11, 12, and 15. 13 and 14 are two special topics. One of them deals with benzyne. As the name implies, it's a 6-membered ring with alternating single and pi bonds, but one of them is a triple bond instead of a double bond. And obviously that's under our ring string, but it's a special topic. We're not going to talk about it. It takes time. So that's the only changes really that I still wanted you to see. Okay, now as far as the problem set goes, I mean, tomorrow we can answer questions, but if you have any today, I'd be happy to go over them. But then I realized I brought the wrong book, so I don't have my copy of the problem set with me. I'd have to borrow yours.
Oh, wait, I have two.
Oh, I'm sure you got a spare. How would you end up with the next one? You printed it off?
That's your hard copy.
Oh, okay. Let's see here.
Oh. What's that?
I don't know. That's answer key to the exam or something. But so the problem set, let me get this straight. You guys are working on chapter 14 or 15 right now?
14.
14. I haven't given you 15, eh?
No.
Oh, what? That's a bummer. Did I promise to email it to you? You did?
No.
No, but we gotta get that to you. So after class today, if I actually think about it, I will email it to you, post it on Blackboard. And then tomorrow, I'll bring you a hard copy of it, and going back to the schedule, your exams on Wednesday, and Tuesday is fluff day, so what I'm thinking is, we'll have to make it due Monday or Tuesday morning.
Our exam's Thursday.
So yours is Thursday? Oh.
Yeah.
I'm thinking of my other class, yeah, Molly would kill me. So in that case, Wednesday, well, let's just look here, I've got it, I'm trying to go out memory here, my mind is kind of screwed up. So, Wednesday is the fluff day then, that's review makeup day. So what we'll have to do is make the problem set due like end of day or whatever on Tuesday so that I can get it graded, get it back to you here for Wednesday to go over any questions you have. So yes, I'll send you the problem set for 15 in a bit after class at some point. Get it to you. So, but back to chapter 14. I know you had a question on that, Olivia. You want me to go over here?
I have 2 questions, but I guess you could go over
Question.
22.
22. Okay. Alrighty. Says which of the following substances, and so we're given these different formulas here, would exhibit 5 signals on its C13 NMR. So that's not that difficult. I mean, this is very straightforward, let's just say. So what we're doing is we're looking at these structures, looking for one that has 5 chemical shift different carbons. And we're looking for 5. That's actually quite a few. So let's, like, for example, look at 1 here. Normally I like to try to leave things out, but let's just look at 1. There's really no symmetry at all in this thing. And so that carbon, for example, is different than this carbon, right? Because of lack of symmetry, that would be 1 signal, 2 signals. And then every carbon in this ring is different. There's no symmetry there whatsoever. So it turns out that this one would have 1, 2, plus 6 more. It would have 8 signals. 8 different carbons. So it's not that. It can't be that one. We look at this here. Yeah, same thing. Due to a lack of symmetry, it's going to have 8 as well. So 1, 2, and 6 for those. It's not that guy, it's 8. So seeing some symmetry here with this particular one, let's see what we've got. Of course, these methyl groups are symmetric to one another. There's a plane of symmetry here. So we get one for the methyl groups, one more for this particular carbon, so that'd be 2. And then these 2 carbons are identical, so that would be 3. And then these 2 are symmetrical, that'd be 4. And then this one would be 5. So it appears to be that. Of course, we could look at the others, but due to lack of symmetry, each of these would have 8 as well. Make sense?
Yeah.
Is that what you thought? You're holding?
And I already got
How did you
it.
get 8 signals?
How do I get 8 signals? Well, let's look here. So take any of them, like this one here. I get 1 for that, 1 for that, because they're not the same. And then there's 6 carbons in the benzene ring. They're each going to have their own signal because there's no symmetry. They're all identical. They're all unique. So I have 3, 4, 5, 6, 7, 8.
Are you looking at the hydrogen on those carbons?
We're not doing an HMR, it's carbon.
Oh,
CMR, yeah, there you go.
okay.
Yeah. If it was, now let's look at, say this one, either of these, because I haven't butchered them up. If we were looking at carbon signals, it would be 7, I guess, because we have one set of protons here, that'd be 1 signal, 1 signal here. You have carbon there, actually, I guess it would be 6. So you have 1, 2, 3, 4. Oh, 5. Yeah, it'd only be 5. It'd be 5 proton signals on that, but 8 carbon NMRs. Okay, you said you had another one, and then we'll
19.
move on here. 19. All right, so 19. Which of these would you expect to have significant resonance stabilization energy? All right, now significant would be also known as aromatic, right? That's what we're looking for here. Obviously, this guy here, being benzene, is going to have a bunch. Looking at this one, it's got a couple of lone pairs on it. One of those lone pairs could be in an unhybridized p orbital, the other could be in an sp2 hybridized orbital. So it looks like we would have 2, 4, 6 pi electrons. It's cyclic, it could be planar, all the above, so it's aromatic Buckle number, right? So it could be that one as well. And then this guy here, got a lone pair of electrons that are going to be in an sp2 hybridized orbital, because this pi set of electrons is using the p orbital. So we've got 2, 4, 6 pi electrons. It's a Huckel number. It's cyclic. It's every carbon or every atom's got a p orbital, so it could be 3 as well. So it's all the above. D. Now, if the question says which would have the greatest resonance stabilization, that'd be hard to get that data to back it up. But they're all aromatic, so we're all going to have significant. All right. Like I said, tomorrow we'll finish this up. Hopefully, you guys will get a chance to get started on chapter 15. Problem set. You want me to keep this sheet or?
You can keep it.
All right, so I can bring it to my 122 class and get it out today and use what it does. I've been doing that a lot lately. You get yourself caught up thinking 10 minutes ahead or something. So I still have the problem sets in my book. I haven't handed them back yet. And so then I asked them, I'm like, well, do you guys have any questions on the problem set? And they're all kind of looking at me and I'm like, what? I graded it. You guys got a lot wrong. You should have a lot of questions. And they're like, you didn't hand it back yet. Okay, hand it back. I haven't done that yet. Thought I did. All right, so we are, in section 9 here, because yesterday we had talked about the ortho, para, and meta-directing groups. And I got asked, did you guys go home and try to sort that out and figure out kind of what's going on? Did it make enough sense that you think you can do something with it, work some problems out? Yuki?
No.
I know you're laughing under that mask.
No.
What, do you have any questions on it? I mean, is there anything that I went over yesterday, like electron donating group, withdrawing group, resonance?
I think I'm okay.
Okay. So it didn't sound like you were okay a couple seconds ago.
No, I was studying math last night. So
Oh, math?
I didn't review.
Differential equations, that's. I saw Mr. Ruffin Hall the other day. I said, I heard you're making differential equations too easy. And he says, we'll have to do something about that. So, I was kidding.
I got him to cancel.
So yeah, we had 2 questions yesterday that we set out to address. One is, how do the substituents on a benzene ring, one or more of them, affect regiochemistry, and so we talked about the ortho-para-directing groups, the meta-directing groups, and what we said was that if it's an electron-donating group, it's always an ortho-para-directing group. If it's a halogen, it's also an ortho-para-directing group. And then we said that if it's an electron-withdrawing group, then it has to be a meta-directing group, no exceptions. If it's electron-withdrawing, with the exception of the halogens, I guess, which I already talked about, then it's a meta-directing group. Now, the second question that we needed to answer is really the easier one of the two because it's pretty straightforward. And that is, how do the presence of existing substituents affect reactivity? In other words, we're talking about benzene ring that we've already said is relatively unreactive, right? And these 5 reactions that we're looking at are like the only reactions that we can do of any use with benzene, other than combust it or hydrogenate it. And so it's already not very reactive, so we're kind of curious to know, can we make it more reactive? Can we make it less reactive with a substituent? And the answer is yes, and so that's what we're going to look at here in this section. So in general, what we're talking about is we've got a substituted benzene ring here. We're saying why. It's got a substituent, either electron donating or withdrawing. That's pretty obvious, but we've got ourselves a substituent. Now we're going to ask the question, when it reacts with an electrophile to give us a product, and there again we're using this line that comes out of the center of the benzene to show a lack of stereospecificity here. We're not saying where this group is, we're just saying we've added it and substituted it somewhere. Will this reaction right here, because of this substituent, be faster or slower than this baseline reaction of just benzene reacting with an electrophile? So that's the question. Does a substituent make this reaction faster or slower than this reaction here? And there again, it comes down to whether Y is electron donating or withdrawing. It's really easy. If it's an electron donating group, it's going to be faster. If it's an electron withdrawing group, it's going to be slower. That's what it comes down to. And there again, we have the regiochemistry aspect. This slide should have been yesterday. I don't know why I left it down here. I moved it. But just to refresh your memory from yesterday, the other question that we talked about is, with that substituent Y in there, not only are we interested in this, the reaction faster or slower, but where is it going to go? Is it going to go in the ortho position, the meta position, or the para position? So, okay, review from yesterday. But now back to this. We're looking at specifically what happens when we've got the group on here, be it electron withdrawing or donating group. We're reacting it with an electrophile, partial positive charge. Never is it a free cation. It's always somehow turned into a cation through a catalyst or whatever. And so we're removing that electrophile. Now you've lost the aromaticity. You've got a positive charge, and this is what's important. Is that because this is the rate determining step, and it does involve a positive charge on the benzene ring. If this group is electron donating, it can tend to stabilize this. If it's electron withdrawing, it destabilizes it. So for that reason, if this is electron donating and this is stabilized, the reaction will be faster. But if it's electron withdrawing, it makes this thing worse. It's going to be slower, right? So we're looking at essentially is 3 cases for the rate determining step, where we've got our first step, right? This would, we'll say, be with just benzene. If it's got electron donating group on it, this would be DG. It's a lower activation ring, so it's going to be a little faster. And if it has an electron withdrawing group, then it's going to be slower. That's what's happening. We're looking at 3 different curves here for the rate determining step. They each have different activation energies, because if you're going to end up with a less stable intermediate, then that activation energy has to be a little higher. It's going to be a slower reaction. Okay, so as far as reactivity goes, now we'll get into specifics. It says, since electrophilic aromatic substitution is electrophilic, in other words, you need to have a benzene ring that's electron rich to react with this electrophile, which is looking for electron density. Then the rate determining step is the attack of an electrophile with the benzene pi electrons. So an increase in the electron density of the benzene ring will increase the reactivity of the aromatic ring towards an electrophile and result in a faster reaction. Faster because activation energy is lower, right? Remember, what can we do to affect the rate of reaction? activation energy, which really can't change much, catalyst, and temperature. We're not varying catalyst or temperature here, we're only varying activation energy. It's the only reason it would be faster. Another point you made here with reactivity is that on the other hand, the decrease in the electron density of the benzene ring will decrease the reactivity of the aromatic ring towards the attack and the electrophile results in slower reaction. So we're talking about this guy up there. Electron withdrawing group decreases the electron density where we want it, and that's in the pi electron region. Okay, another slide here, just kind of keep trying to show you the basics. Like I say, this topic of electron donating and drawing group was really supposed to be the first topic we were talking about before we got into all the directing groups. And so there's a lot of kind of basic things here. If Z is donating electron density to this benzene ring, it makes it what we call activated. Right, so here's a new term for you. Electron donating groups will activate the benzene ring and make it more reactive. Whereas an electron withdrawing group will deactivate the benzene ring. So in chemistry, specifically here with benzene in this example, when we say activating, that's usually pumping electron density into something, and deactivating is withdrawing electron density. Usually what it means. So here we have it as a relative comparison. If our benzene ring, if the group that we're referring to is just another hydrogen, in other words, it's unsubstituted, benzene is the baseline here. If we have an electron donating group, it's going to react faster. If we have an electron withdrawing group, it's going to react slower. I think this is the fourth slide that said the same thing. Right? I'm not even talking about stereochemistry, we're just talking about the rate of reaction. And that's why, like yesterday, there was a few things that we couldn't help but talk about because they do depend on what we're talking about today. And that is, if you started with, say, benzene, and then you alkylated it, and you got this. Alright, so you got some alkyl benzene. This is an electron donating group. Electron donating group makes this thing more reactive now. And so if you've got a mixture of benzene and alkyl chloride, you're doing a Field-Crafts alkylation, as you produce more and more of this, which is more reactive than this, then it's more likely that this is just going to undergo successive polyalkylations, and now you're going to end up with that, and pretty soon the whole thing is going to be substituted, right? And it's because this is more reactive than this, which means this is going to form this. Well, now this is more reactive than either of these two, so it's going to become trialkylated, and it's going to get carried away. So they are really like this concept of stereochemistry and how many alkylations am I going to do and reaction rate. Likewise, if I were to nitrate this guy here and nitrate it, well, now that I've nitrated it, I've deactivated it because the nitro group is an electron withdrawing group. It's got a positive partial charge there. Not a partial charge, but a formal charge of positive, negative formal charge there. So these electrons in the pi system want to go out and form a double bond with the nitrogen, and that deactivates it. And so what happens is now, this is actually sort of a good thing in terms of yield, selectivity, and all that. If you start with benzene and start nitrating it, every time you nitrate a benzene ring, this is a whole lot less reactive than the remaining benzene. And so you're not going to polynitrate it. Not going to happen. Right? Not unless you have an excess of it. So in summary, electron donating groups increase the electron density of the benzene ring, move the reaction towards the products in a faster fashion, and they also are ortho-pair directors. You might as well just make note of that. Ortho-pair directors. Electron withdrawing group. They withdraw electron density from the benzene ring, they decrease the electron density, make it less reactive towards our electrophilic aromatic substitution, and they are meta-directing groups. But probably more important is that you got to remember what these groups are, which ones are they. So if I started drawing some groups up here, and this is kind of the basic stuff that we need to know here, is are they electron donating withdrawing? So for example, if I've got an OH group, Electron donating or withdrawing? So how quickly it gets kind of confusing, because if you sit here and you think about it, you say, well, here's benzene ring. You say oxygen is more electronegative than carbon, so therefore it's drawing electron density towards it, so you'd say, oh, it's electron withdrawing group. But then you look at the lone pair electrons and you say, well, I can donate those through resonance, so it must be electron donating, so which one is it? And that's where yesterday we said that when this atom and this atom are in the same period on the periodic table, which they are, same size roughly, then this mesomeric or resonance effect is more important than the inductive effect, and so this is an electron donating group, right? Electron donating group. What about this guy? These are just some things that we talked about yesterday. Electron donating or withdrawing group?
Drawing.
Certainly a withdrawing group, for two reasons. One, through resonance, I can pull electrons out with positive charge on the carbon, which is going to draw electrons towards it. Furthermore, because I've got an electronegative element out here, through induction, it's going to try to draw electrons. So both effects are working against the benzene ring here, and it's definitely going to be an electron deficient group, or ring, as a result of that. So you'll have questions that'll say, which of the following are most reactive towards electroaromatic substitution? So you'll start looking at different groups, and so now maybe you'll have something like this. And this is the kind of question we need to answer today. What if I had this here? No, we'll put a halide in here. And now over here, I'll put, let's say, a methyl group. What's the net result? Is that ring activated or deactivated? Because what have I done here now? I've thrown on two substituents, not just one, but two. And so this is what we're going to talk about in a little bit. When I look at fluorine, fluorine is a electron withdrawing group. It's an ortho pair director, but it's electron withdrawing group. Whereas methyl group is electron donating. So what is it? I got one group that's pulling electron density from the ring, and I got another group that's donating electron density. Do they cancel out? Is one more important than the other? I want you to think about that. We're going to get to it. I want you to think about it. So we're heading towards your split. Okay, so here's about the 15th slide in a row that says if you've got an electron donating group on your benzene ring, it's going to be more reactive than just benzene, which is going to be more reactive than a benzene ring that has an electron withdrawing group on it. Pretty straightforward. Probably very important because we're spending a lot of time showing you the same stuff. All right, here is another table that summarizes these different types of substituents, and I've also included whether they're ortho-para or meta or what have you. And so you can see at the bottom here, this is the baseline, hydrogen. It's neither activating nor deactivating, it's neither ortho-para or meta-directing, right? It's the baseline, it's indifferent. Everything else on this table is what we call electron donating groups. So we've got the amino groups, hydroxyl group, which we just looked at, even an oxide. I know it sounds funny, but if you got just an oxygen there, it's an oxide, like a deprotonated phenol, right? Something that you had in the lab here a few weeks ago. You say, well, it's got negative charge. It must be pulling electron density from the benzene ring. No, it's not. Actually, it's got an excess of charge, and it would just love at times to kind of share it with the benzene ring. So through resonance, it has all kinds of ways to donate electron density. Even though it's more electronegative, you might say, well, through induction, it's pulling electron density away from the ring. No, it's not, because the overall effect is that it's donating through resonance. So yes, an oxide is also a donating group. And then we have, what's this group here? What would this be? It's another amino-based group, but I guess I need to draw it for you here. So you've got NHCOR. That means you've got N, H, and then C, OR, one pair of electrons there. That's what it is. Right? It's amino ether. but still, has a pair of electrons that it can donate to the benzene ring. So here's the benzene ring, it can donate. I told you, if the atom that's directly bonded to the benzene ring has at least a one pair of electrons on it, regardless of what else it's bonded to, it's an electron donating group. Even if it's fluorine, still electron donating. Alkyl groups, another phenyl group, or another aromatic group. So if I've got a benzene ring bonded to another benzene ring, what we're saying is that overall, well, then you're kind of guessing here as to which ring is going to get substituted anyway, but let's just say that we're going to do the substitution on this ring. The fact that I've got this, it's still treated as an electron donating group, right? It actually, between the two, they actually activate one another. All right, here are your electron withdrawing groups. So that would, we said the halogens are slightly electron withdrawing, even though they're orbital pair directors. Slightly, right? So they donate electron density. All right, I guess I don't have one drawn here. You have a halogen up here. Because it's in a different period than the carbon is, it turns out that the inductive effect is a little bit more important than the resonance effect. But the resonance effect is still there, and that's why it's orbital pair directed. But before you even get that carbocation form, this ring is actually slightly deactivated because of the inductive effect. It's just that once the carbocation forms, like there, then through resonance it can stabilize it. So that's the exception. And then the rest of these all involve an atom for the most part. So if you got your benzene ring, and then there's some atom here, X we'll call it, that either has a double bond to it, or it's bonded directly to something very electronegative. Those are your electron withdrawing groups, because that double bond through resonance can kick out with a positive charge on it, which is going to draw electron density towards it. Or if it's bonded to a bunch of electronegative groups themselves, oxygen, whatever, through induction, it's also going to be pulling electron density towards it. So a couple up here that I just want to show you would be like the cyano group, CN. So if you've got your benzene ring and it's bonded to a cyano group, we need to think about what the Lewis structure of that looks like. Right? Cyano group is that. That's actually a really serious electron withdrawing group because it has the potential for a couple of pairs of pi electrons to go up. We're not going to do that, but you could draw a resonance structure that actually puts a 2 positive charge on the carbon. Right? This is a very serious electron withdrawing group. But probably the most strong, and you can see it down there, is this nitro group. And that's the one I wanted to show you here. The nitro group is probably the most deactivating that you're going to need to worry about. And that is because, there again, you already have charge separation in one of the resonance structures. So there's a positive charge on the nitrogen from the get-go. You can't get rid of it. Plus, you could imagine doing that, which would put a 2 positive charge. So nitro group is very electron withdrawing. So it's strongly deactivating. Not only that, it's a very strong meta director. Right? So if it's very strong in this department, it's also very strong over here. So, questions on this? Does it make sense? I don't want you guys to just fall asleep here. It's very important stuff. All right, now back to that original question that I asked a little bit ago, and that is, well, all right, all these things we're looking at are mono-substituted benzene rings. Now what happens if they're di-substituted or tri-substituted, okay? And what if the groups that are on are conflicting? What if I got an electron donating group and then also an electron withdrawing group? And here's the answer to it. The directing effect, right, directing, we're talking about stereochemistry now. The directing effect of the electron donating group usually outweighs that of the electron withdrawing group. So with that said, if I've got this example, so I've got a nitro group here, very strong deactivating group, meta directing group, the whole 9 yards. And over here now, I've got, we'll say, an alkyl group. right? Electron withdrawing, electron donating. What we're saying is that even though this is a strong electron withdrawing group, and this is a mediocre donating group, this still takes precedence. We don't care about this. Yes, it's a deactivating group, but we don't care about it. This is what matters. So because this is an activating group, and because it's an ortho-para director, ortho would be that position and this position, but we can't go there because it's already a nitro, and here's the para position, para to it, right? So the fact that we've got this electron donating group determines the locations that are possible as far as the substitution goes. So don't pay attention to whether it's strong or weakly activating or deactivating. That's not important. What matters is if you've got an activating group, it takes precedence. Now what if you got two or more activating groups? Now is where you got to think about the strength of it. So if I've got two or more activating groups, like say I've got, let's see here. So I've got an amino group here, and I've got an alkyl group there. They are both activating groups, electron donating groups. This one does it through induction. This does it through resonance. So we said the activating group always takes precedence, but they're both activating groups. So now you got to find a way to break the tie. So you look at the stronger activating group. Because this does it through resonance and this doesn't, this one takes precedence. So we're going to just kind of like pretend this isn't here. And we're going to look at the positions that are ortho-para to this, not this. Right? So positions that are ortho-para to this would be here, which I can't go, so I've already got an alpha group. Or I could go here, or I could go there. So we've got it pretty much figured out as to where the substitution would take place based on the strongest of the two activating groups. So it says here, second point, with two electron donating groups, the directing effect is usually controlled by the stronger. Change the words. With three electron donating groups, the directive effect is controlled by the stronger. So you're always looking for the stronger if there's more than one. All right, now what we got are several examples. I think there's 6 or 8 of them, something like that, where we just look at some reactants and predict the location of the product. We're not so interested in how quickly it's going to take place. Some of these reactions will be a lot faster than others, but we're just looking at the product itself. So in this case, I'm trying to nitrate this thing, right? Anybody want to take a guess at what you'd call this? If those are 2 or 3 hydrogens, that means you got 2 methyl groups on a benzene ring. What do you call it when you got 2 methyl groups on a benzene ring? What's that called? Not toluene. Starts with a Z, not a Z, sounds like a Z. Starts with an X. Xylene, right? So it's a xylene. This would be paraxylene, but because one of them has 3 fluorines, we call it trifluoroparaxylene, right? So that's what we've got here, trifluoroparaxylene as our reactant, and we're trying to nitrate it. But what do I have? What type of group is a methyl group? Activating or deactivating? I like that word. It's activating, right? Donating electron density. This is a what type of group?
Deactivating.
Yeah, halogenated methyl group is deactivating. And so between the two here, activating, deactivating, even though this is probably a stronger deactivating group than this is an activating group, we still base everything on this. Right? So relative to this, the substitution is either going to be ortho or para. It can't be para because I've already got something there. So it's going to be one of these 2 positions, and they're symmetric, so it doesn't matter. And that's why it ends up there. Right? Very predictable. Next one, got a methoxy group, and then I've got this thing here. What's this? I was hoping we wouldn't say that. Now, if you look at it, this carbon doesn't have any hydrogens on it. So it's just bonded to this carbon and apparently to this and then to this. That's a double bonded oxygen. This is a ketone, right? This is a ketone. This is a methyl and then whatever you call this, ketone. So there's a double bonded carbon here. Double bonded carbons are what type of groups?
Withdrawing.
Withdrawing, yeah. So we got a withdrawing group here and a donating group here. Donating group takes precedence, so just pretend this isn't here. Because it's a donating group, it's going to be ortho-para. So ortho, can't be here though. It's already taken care of. You've got these two. Now, given the choice, we talked about this yesterday, given the choice that this, by the way, we're brominating, could either go here or here, which position do you think is going to be more important? Probably the major product. Why? Here or here? The answer is here, because it's near kindreds, right? It's further away from these guys. Now, bromine is a pretty small atom, compared to like a methyl group or whatever. So it's also going to go here. You're going to get a mixture of the two, but you probably get more of this. So this product over here, I would predict to be the major product. Now, if it comes out being the minor product, that doesn't make sense. We got to figure out why. And then I would expect this to be the minor product. Okay, so with this example here now, we've got some other things we need to think about. It kind of carries over from what I just talked about with steric hindrance. When you've got, in this case, dye substitution going on in this position, and then this would be meta to it, so we'll call it meta substituents to one another, 1,3. When we're looking at both of these are both slightly deactivating groups, but they're also both ortho-para-directing groups. So this position is ortho to this chlorine and this bromine. Right? That position is ortho. This position is ortho to the bromine. This is ortho to that, and this turns out to be para to both of them. But what we're saying is that even though there's nothing here in this meta position, we're not going to put anything there because it's squished between these meta, or this is an ortho position of both of these, but we're not going to substitute here because it's squished between these two meta substituents. So when you look at the products, you're going to get them all over the place. Right here, which is meta to this, or ortho to this, and para to this. You're going to get nothing here because it's squished between the two, and then you'll get some here because it's ortho to the bromine. But it's also para to the chlorine as well. But we're just saying that you're not, just like the back here, what I'm trying to say is probably the major product, probably the minor product because of steric hindrance. But if you think this steric hindrance is an issue, it's a bigger issue here because it would be squished between two substituents, not next to just one, but between two. So the data says 1% yield, and you can explain why. As far as trying to explain why this is 37% yield and this is 62% yield, that's a little bit harder of an explanation because to me, who's a bigger atom, bromine or chlorine? Bromine's bigger, period 4, I think, versus period 3. And so you, in my mind, expect this substituent, given the choice, to be closer to the smaller atom, not the bigger atom that it is. So there's something else going on. And we have to think about what it is and try to explain it, but for now, don't worry about it. Another example. So I've got this amino group here, but it's got this COCH3 bonded to it. So it's, in this case, that's just that. It's just what I think I drew up here. I want to make sure it was the same concept. So you got a benzene ring, and we're looking at the top there. So it's a nitrogen, lone pair, hydrogen, oxygen, CH3, something like that. Amino ether, but still, lone pair of electrons here, activating group, so it's an ortho-para director. And then down on the bottom right-hand side, down here, you gotta watch that guy. That is an ester. So you got a double bonded oxygen, a single bonded oxygen, and then a methyl group. So through resonance, you put positive charge there, which is going to suck electron density away. Our activating group is on top. Deactivating group is here, so we just pretend this isn't here in terms of the directing effect. So now we say, okay, our substitutions are going to be ortho-para relative to this group. Ortho, but not here. That's squished between two groups. We said we can't do that. So it's only here or here. One of these two. And that's what we get. Down here, that'll be the para. Over here would be the ortho position. Let me ask once again, how would you do that? Making sense? Alright. It is so hard, especially like I said before with these masks on. I can't see what's on your faces. But usually that's something you look for. If I say something, everybody's like, then I know it's not going over well. If I'm saying something, they're like, then it's obviously get it. Can't tell. So I don't know anymore whether students are following or not. Here's example 4. So what do we have? We've got this methoxy group, click on donating or drawing. Huh? Donating, yes, to residents. And then what do we have here? Methyl group, donating or withdrawing? All right, which one's stronger?
Methoxy.
Methoxy, because it can do it through residents. That's the only way it does it. Because through reduction, it's a withdrawing group. So this is a donating group through residents. This is a donating group through reduction. This is more important. This is stronger than this. And so this one takes precedence over this one. If this takes precedence, it's going to be ortho pair director. So ortho, but not here, so we have something there, or pair. So it better be in these 2 positions. And that's what we see. Down here is the pair. You notice I'm not even paying attention to what we're adding or what we're substituting. We don't have nitro, sulfonyl, whatever. This thing might do. So here we've got example 4. So we've got a chlorine group. What can you say about that? Activating or deactivating? Slightly deactivating. It is an ortho pair director, but it's deactivating. And then what do we have here? Ooh, another deactivating group. So now what do we do in this case? I didn't talk about this one. What if we have 2 deactivating groups? Who takes precedence? I mean, seriously, this is an important question because on an exam you'll forget. In some ways, logic tells you that if you have 2 deactivating groups, the one that's the strongest deactivating group is going to take precedence. But what was the rule before? The stronger activating group takes precedence. And so really, it's the less deactivating group that takes precedence. And so the less deactivating group happens to be the chlorine. And because it is an ortho pair director, we have to look in the ortho pair positions. So ortho pair, but we're not going to put anything here because that's between 2 meta positions, so we can't do that. So we're really left with these 2 positions, and that's why we end up with 1 there and 1 there. Okay. So you can have a lot of fun with this stuff. You just got to apply it and remember what the rules are. The material for the day. So there again, tomorrow I guess I don't plan on starting anything new as far as jumping into the next sections, although I might, if you guys are willing to have questions. I'd rather go over questions from the problem set for 14. I'd rather go over questions from the problem set that I'm going to email you shortly or post on Blackboard. So I don't expect it to be a long day, maybe hour and a half. I also realize that the week before spring break, our attention span is about 5 minutes. I'm going to try to exceed that by a whole lot. Okay, so have a good day. If you find my outdrive somewhere, let me know, by the way. Nice. I think I already did.